Hello everyone and welcome back. I'm Mr. Cobalt, and in this video I'm going to talk about thermal energy transfer. And so this is where you have a situation where you have a hotter object and you throw it into like a colder solution, or maybe you put the two objects together and you get a heat transfer. Or another thing you could do is, or another situation you could have is that you have a reaction going on in a reaction vessel of some sort. So maybe it's in a beaker of water, or maybe it's a solution, or you're mixing two solutions together, and the reaction occurs when you mix them together. Or you're burning something in a bomb calorimeter, and you've got the heat being involved from the reaction, and it's being absorbed by the water in the bomb calorimeter and the calorimeter itself and things like that. So you got some sort of heat transfer going on. Something's being absorbing the heat, something's giving off the heat. And so those are types of problems that you're going to have to solve in your chemistry class or some other science class that's involved thermodynamics. And so the key here is to always remember that the energy given off or absorbed by the system is going to be the same amount, the same magnitude as that which is being absorbed or gained by the surroundings. So that's the really key here. But the hard part is, especially for the tricky problems, is keeping track of everything that's involved in the heat transfer. Okay, but I'll get to that in a moment. But so here the thing is that if you've got a simple problem where you're throwing a hot object into, say, a glass of cool water, so that's a typical problem you're going to run into. So I have a hot, high temperature, like maybe it's 100 degrees Celsius or whatever the case may be. Maybe it's 65 degrees Celsius, my block, and I put it in 25-degree water, right? So I put it in the water, and then of course, as we saw before, that heat transfer always goes from the high temperature to the low. So some of the heat from the block, some of the thermal energy from the block is going to be transferred to the water, heating up the water, right? So the water will raise its temperature, the block will lower its temperature until you reach the same temperature of the block and the water, and that's when you reach that thermal equilibrium, right? So in that case, then you have a transfer of heat from one object to the other. So you got to figure out what your system and your surroundings are. So in that particular instance, it's really simple. Your system, let's say, is the block, right? So you're focused on what's happening with the block. Is the block losing energy, gaining energy, or whatever? So, and then the surroundings you would be told is the water in the beaker, or the beaker itself, if you're told heat capacity or specific heat capacity of the glass in the beaker and the mass of the beaker and stuff like that. But a lot of times you're going to ignore the beaker. So make it simple. So you've got the water is the surroundings, and the block of metal is going to be the system. So so if you're given the specific heat of the water and the specific heat of the metal, then again, what I said before is if you know the specific heat of the object, remember that specific heat is going to be, the units are going to be joules per gram per degree Celsius. So remember, the units are going to give you the equation. So remember, Q is referring to heat energy, right? Or thermal energy, right? So here we want energy units. So to get energy units, you look at your specific heat, and it says, well, if I want energy units, I need to multiply by grams to cancel out grams. I need to multiply by a temperature change to get rid of degrees Celsius, right? So then what it would look like is I would replace Q of the system with the equation. The general equation we said was Q is equal to mass times the specific heat times the change in temperature, right? So multiplying by mass, multiplying by change in temperature will get rid of grams and degrees Celsius, leaving only the energy unit of joules, right? So if I'm given like a block, my system is a block, then I can use the information, the mass of the block, specific heat of the block, and the temperature change of the block, right? For one side, so then I would have, so for this one, it would be, I would have Q is equal to the mass of, say, the block, I'll put block, multiplied by the specific heat of the block, multiplied by the temperature change of the block. So remember, final minus initial. And then for the surroundings, which in my hypothetical is the water. So that would be Q, same equation, because I would have the mass of the water somehow, the mass of the water, specific heat of the water, and I would have the temperature change of the water as well, right? So that's going to be then again mass of the water, H2O, multiplied by the specific heat of the water, H2O, times delta T of H2O. And then so if I know these two, and I know that this is Q of the surroundings, and this is Q of my system, then if the Q of the system is equal to the Q of the surroundings, then I can set those equal together, right? Q, oops. So I would have mass of H2O. Let's write this. So this would be mass of the block multiplied by the specific heat of the block multiplied by delta T of the block, right? And if I expand this, let's expand this. This is going to be the initial temperature of the block, or I should say final temperature of the block minus the initial temperature of the block, right? And then that's going to be equal to the Q of the surroundings, which is the water. And so I would have the mass of the water multiplied by the specific heat of the water. And then if I expand that, that's going to be the final temperature of the water minus the initial temperature of the water. Now that I have the equation, then it's just a matter of putting everything in that I am given. So if I'm given the mass of the block, I could put that in, the specific heat of the block. Maybe I'm given the initial temperature of the block, but not the final temperature. Maybe I need to find the final temperature. And then I have the mass of the water as well. Sometimes they might give me density, right? So they might give me density and volume, and I'll need to use that to find the mass, right? So they can throw things into you like that. Watch out for that. So if they don't give you the mass of the water, then they'll probably either you need to find the mass of the water that in the problem, or they give you some information to help you find the mass. Like I said, density and volume. The specific heat of the water, and again, if they don't give you the final temperature of the water, which is going to be the same temperature as the block, right? So those are going to be the same temperature because they're reaching equilibrium, which means same temperature. And then they give you the initial temperature of the water. So in a lot of these problems, they'll ask you to find the final temperature of the system. You might be asked to find the mass of something as well. So it just depends on what they give you and what they're asking you to find. Okay, so one of the things I want to say as well is this is a good way of putting it, but I think there's a better way of solving this because this can get complicated really quick because you can have a complicated system, right? So the system could be that here in this problem, the system was really simple. The environment was really simple. You only had one thing to worry about in the system. That was the block. You only had one thing to worry about in the surroundings. That was the water. But what if you have multiple things that are going on, right? So you could have a couple of things giving off energy. You could have a couple of things absorbing the energy. So you have multiple things that are absorbing and giving off energy. And you need to account for all of that when you're doing a thermal energy transfer problem. So, for example, you could have a reaction in a solution, right? So if I have two beakers, right, two beakers of different solutions, I mix them together and that produces a reaction, right? So I have the reaction, so I'll need to know the delta H, the standard thermal enthalpy, the enthalpy of reaction, right? Of whatever the reaction is going on. So that's going to be the heat evolved or absorbed by the reaction, right? So I'll need to know that. So that's a source of energy being transferred. So the solution that the reaction is occurring in is also part of the surroundings. So they might give you the heat capacity of the solution, they might give you the density of the solution. And so you'll need to figure out, well, that's part of the surroundings, so that's going to absorb some of the heat as well, right? So you might have the solution involved, right? Solution. Let's say you've got a beaker of ice water, right? And you've got a certain amount of ice in the water, and you've got a reaction occurring in the vessel as well, right? So maybe some of that heat is going to be absorbed by the water, by the ice, and that some of that melts, and then you're going to have to figure out the mass of the ice that's melted, right? So you have to take in consideration that as well. You also have a calorimeter, right? So if the reaction is occurring in a calorimeter, some of that energy is going to be absorbed by the calorimeter because that's part of the surroundings as well. So you've got the solution as part of the surroundings, you've got the calorimeter as part of the surroundings, you might have ice as part of the surroundings, right? And then you have the reaction, which is the system. The reaction of the system is usually the reaction itself is usually the system, and the reaction and the solution in which the reaction is occurring are different things. So the solution in which you have the reaction is part of the surroundings. The reaction itself is usually the system that you're focusing on. So you're focused on like the heat of the reaction. Is it giving off heat? Is it absorbing heat? Now, to make this a lot simpler, this is what I suggest. Instead of writing it this way, you should write the equation as this way. 0 is equal to Q of the system plus Q of the surroundings. And these are going to be opposite in opposite in symbol or negative. One's going to be negative, one's going to be positive. And so if you write it this way, then all you need to do is remember what your different Q values are, because certain things are going to be absorbing heat, certain things are going to be giving off heat. You don't need to worry about the symbol or the sign of each one. So you could have 0 is equal to Q1 plus Q2 plus Q3 plus Q4 plus ... right? And so all you need to do is just make sure that you're keeping track of each thing that's involved in the heat transfer. So maybe one of these Q's is going to be the delta H of the reaction, right? And so remember, delta H of the reaction is going to be in terms of probably kilojoules per mole, right? So what you need to get rid of moles, so you need to figure out what equation you're going to use to get this Q value. And maybe this is the Q value of the solution, right? So you have to figure out like what equation you're going to need to use to get that Q value. So maybe that's your mass times the specific heat times the change in temperature. Or maybe this here is your calorimeter, right? So your calorimeter is going to absorb some heat. So you just need to figure out what the Q values are, what the signs are, negative, positive, and then what you end up doing is adding them together and solving for the missing part.